This is lecture 12 already, almost halfway through the semester. And we'll be talking about the Euler phi function. But before we start, are there any questions about homework problems or any of the material we've been discussing?
Yes, I had a question, but let me.
Yes, what is the question?
It's from the last question. I think it was question 7 from the last homework, question 7.
What section?
Give me 1 second. Let me just look at the page so I can tell you what page is it. Sorry. It's about the last thing we did, linear congruence, and that 2.2. And let's see, I think it's this page. No.
So linear congruences is section 2.2. And what problem should I do?
Yes, it's problem, for example, problem 7. The one that say prove that if m is composite and m is not equal to 4, then n minus 1 factorial is congruent to 0 mode n.
Okay. So I said this is the converse of Wilson's theorem. So maybe I'll start by proving Wilson's theorem. And I'll start that by reminding everyone of this very important theorem on linear congruences, which is theorem 2.2. So you have integers m, a, and b with m positive. A and b don't have to be positive. Let d be the greatest common divisor of a and m. Then the congruence, ax congruent to b mod m. So this is solving just a simple linear equation, mod m, and this is solvable. There's an integer, at least one integer x, that's a solution of that congruence, if and only if b is divisible by d. In other words, b is congruent to 0 modulo d. And if in this case, if b is congruent to 0 mod d, then this congruence it always has infinitely many solutions, because if x is a solution, any number congruent to x mod m is also a solution. So what's of interest is the number of pairwise incongruent solutions. And this congruence has exactly d pairwise incongruent solutions modulo m. So in particular, if the greatest common divisor of a and m is 1, that is, if d is equal to 1, then ax congruent to b mod m has only one solution mod m, has a unique solution mod m. So for example, suppose we want to solve the congruence 7x congruent to 3 mod 11. So in this case, a is equal to 7, b is equal to 3, m is equal to 11, d, which is the greatest common divisor of a and m, which means the greatest common divisor of 7 and 11, that greatest common divisor is 1. So this solution, so this congruence has a unique solution modulo 11. So if 7x is congruent to 3 mod 11, one solution is x equal 2. because 14 minus 3 is 11. Another solution would be x equals 13, because 7 times 13 is 91. Take away 3 is 88, is divisible by 11, but 13 is congruent to 2 mod 11. So these are two solutions, but they're not distinct mod 11. So the solution, the general solution, the only solutions, all solutions of this congruence are all x congruent to 2 mod 11, like 13. So there are infinitely many numbers x that solve this congruence, but there's a unique solution. There's exactly one congruence class mod 11 of solutions, and it's the congruence class x congruent to 2 mod 11. So this is really an extremely important bit of number theory. And it also says it's a corollary that if P is prime, the set of congruence classes mod P, Z mod PZ, is a field. So we know that for all M, the set of congruence classes Z mod MZ. So you have to really, this is very fundamental, you have to remember that this is a finite set. This is just all the congruence classes I plus MZ, I going from 0, 1, 2 up to M minus 1. So this is a finite set, and each element of this set is an infinite set of integers. This is always a commutative ring. But if M is a prime, if the modulus is a prime, Z mod PZ is a field, that means every congruence class has an inverse. So if you take the congruence class A plus PZ, you can always solve AX congruent to 1 mod P, and X plus PZ will be the inverse of A plus PZ, because A plus PZ times X plus PZ is AX plus PZ is 1 plus PZ, because AX is congruent to 1 mod P. So there is a huge amount of algebraic theory embedded in these couple of things that I just went over, and really, the more time you spend thinking about these things, the better. It's really very important. And there's also the following lemma. It says if P is a prime, then what are solutions of x squared congruent to plus or minus 1 mod P? Well, x squared congruent to 1 mod P has the solution 1 and minus 1. Sorry. X squared congruent to 1 mod P. So what are two solutions of this? X congruent to 1 or minus 1 mod P. And so if X is congruent to 1 or minus 1 mod P, then X squared is congruent to 1 mod P. You just square 1 and minus 1, you get 1. So X squared congruent to 1 mod P if and only if X is, so proof. If X is congruent to plus or minus 1 mod P, then X squared is congruent to plus or minus 1 squared mod P, but that's always 1 mod P. So if X is one of these two congruence classes, you have a solution to this congruence. Conversely, if X squared is congruent to 1 mod P, that means P divides x squared minus 1, which is factorable into x plus 1, x minus 1. So P, if P divides a product, it divides one of the factors. So either P divides x plus 1, which means x is congruent to minus 1 mod P, or P divides x minus 1, which means x is congruent to plus 1 mod P. So if you have a solution of this congruence, it has to be plus or minus 1 mod P. Any questions about this? This is, it's not possible to overemphasize how important this is. And then a very nice application of all this is a classical result in number theory called Wilson's theorem, which says that if P is prime, then P minus 1 factorial is congruent to minus 1 mod P. And before we prove this, let's look at some examples. Suppose P is 2. So P minus 1 is 2 minus 1 is 1. So P minus 1 factorial is 2 minus 1 factorial is 1 factorial is 1. And 1 is congruent to minus 1 mod 2. This just says 2 divides 2. If P is 3, P minus 1 factorial is 2 factorial is 2. And 2 is congruent to minus 1 mod 3, because 3 divides 3. If P equals 5, P minus 1 factorial, that's 5 minus 1 factorial, that's 4 factorial, that's 1 times 2 times 3 times 4, that's 24. And 24 is congruent to minus 1 mod 5, because 5 divides 25. What about if P is 7? P minus 1 factorial is 7 minus 1 factorial is 6 factorial. That's 1 times 2 times 3 times 4 times 5 times 6. Let's see. 1 times 2 times 3 times 4 is 24. 5 times 6 is 30. And 24 times 30 is 720. And 720 is congruent to minus 1 mod 7, because the difference, 720 minus minus 1, is 721, is divisible by 7. That's 7 times 103. So if you just check what this says for the first 5 primes, seems to be okay. What about if P is not a prime? What about 4? So 4 minus 1 factorial is 3 factorial is 6, and 6 is not congruent to minus 1 mod 4. So this statement fails. It may fail, and in this case it does fail, if P is composite. So how do we prove Wilson's theorem? So we know it's true for 2, 3, 5, and 7, because I just did the calculation. So that P be, in fact, anything greater than or equal to 5. That's the way I did it in the text. For each A, from 1 up to P minus 1, there's an inverse. such that A inverse is congruent to 1 mod P. And moreover, A equals A inverse if and only if A times A inverse, which is A squared, if A inverse is equal to A, is congruent to 1 mod P, which we just saw happens if and only if A is congruent to 1 or minus 1 mod P. So what this says is the following. If we look at all the numbers, 1, 2, 3, 4, up to P minus 1, P minus 1 is congruent to minus 1 mod P. Except for the numbers 1 and P minus 1. So for all A not equal to plus or minus 1 mod P, we have an inverse, A inverse, which is different from A. So for every number A in this interval of integers, there's some A inverse different from A. So you can pair all these numbers off. So if you look at the product, 1 times 2 times 3 up to P minus 1, you have 1 times P minus 1. And for all the other numbers, you have the number times its inverse. And this is congruent to what? Well, this is congruent to 1. This is 1. This is congruent to P minus 1, which is congruent to minus 1 mod P. That's the proof. Let me do an example just to show what this really means. Suppose I take P equals 7. So I have the numbers 1, 2, 3, 4, 5, and 6. Now, 2, what's the inverse of 2 mod 7? 2 is congruent to 4 mod 7. 3 is congruent to 5 mod 7. So when I multiply these numbers, 1 times 2, so this is my P minus 1 factorial, it's 6 factorial. It's 1 times 2 times 3 times 4 times 5 times 6. I can write that as 1 times 2 times 4 times 3 times 5 times 6. What is this congruent to mod 7? This is 1, this is 1, this is 1. 1 times 1 times 1 times 6 mod 7. That's congruent to 6 mod 7. And 6 is minus 1 mod 7. So this is exactly what we did in the proof. We looked at all the numbers from 1 to P minus 1. This is congruent to 1. This has the inverses itself, but all the other numbers pair off to a number times its inverse mod 7. And we get this. So this is Wilson's theorem, and problem 7 is to prove that the converse isn't true. Sorry, prove that if m is composite and not 4, then m minus 1 factorial is congruent to 0 mod 7. So it's not congruent to minus 1. So this is in section 2.2. exercise 7. Prove that if M is composite and M is not equal to 4, then M minus 1 factorial is congruent to 0 mod M. So we just have to think about what it means to say that M is composite. So if M is composite, then it factors into A times B, with A less than or equal to B, and these numbers are strictly between 1 and M. So let's look at two cases. If we can factor M equal to AB with A different from B, so let's say A is less than B is less than M, then, so what does this mean? This means that A and B are less than or equal to M minus 1. If we look at M minus 1 factorial, 1 times 2, it includes A, it includes B up to M minus 1. This product includes AB, it's AB times something. So this is congruent to 0 mod M. The only time this argument might fail is if A equals B. So suppose A equals B and M equals A squared. Now, if A itself is composite, then A equals, let's say, A1, A2, with A1 less than or equal to A2, less than A and greater than 1. And M, which is A times A, it's A squared, but that's A1 times A2 times A1, A2, which is A1 times this, A1, A2 squared. And this is a factorization where these two factors are different. So the first case applies. We have a factorization of M. It's a product of two distinct proper factors, and so M minus 1 factorial is 0 mod M. So the only time this argument fails is when M is a square and it's the square of a prime. So let's look at that case. So the last case to consider is when M is P squared, where P is prime. So when we look at M minus 1 factorial, this is 1 times 2 times 3, and also P is prime, and M is not 4. So M is at least 6. So P is not 2. P is greater than or equal to 3. So we have M minus 1 factorial. This is all the numbers up to M minus 1 multiplied together. We have P is less than 2P is less than P squared. Right? P is a prime at least 3. So P is less than 2P is less than or equal to, is less than 3P. Which is less than or equal to P squared equals M. So in this product, we will have a factor of p, and we'll have a factor of 2p. So when you multiply this together, you certainly get p squared times something. So this product is congruent to 0 modulo p squared, which is the same as m. So if you take this, look at this problem and break it down into 3 cases, m is composite. It's either the square of a prime or it's not, and you look at the 2 cases separately, and this is the proof. Okay, again, this is mathematics that you might not be used to, or a way of thinking that you may not be used to, but this is what mathematics is, and it's important to learn how to make these kinds of mathematical arguments. Any questions about this? Okay, so then we go to section 2.3, which is the Euler phi function. And the Greek letter phi looks like this. So this is a function phi of n. That's the notation. And, or phi of m, I'll say, where m is a positive integer. So the Euler phi function, phi of m, counts the number of integers from 0 to m minus 1 that are relatively prime to m. It's actually exactly the same thing to count the number of integers from 1 to m. If you don't like 0, they're exactly the same, that are relatively prime to m. So this is a function. So let's start with the table. And I should point out there are 2 typographical errors in the book. So the table is important. So here, m, phi of m, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what is phi of 1? How many numbers from 1 to 1 are relatively prime to 1? 1. What about phi of 2? I'll look at the numbers from 1 to, well, all right. So 0 is not relatively prime to 2, of course, because 0 and 2 are both divisible by 2. So we have to look at just the number 1. I mean, we look at the number 0 and 1 and cross out the numbers that are not relatively prime to 2. We're left with just 1. So there's 1 of them. For 3, the numbers from 0 up to 3 minus 1 are 0, 1, and 2. Cross out the numbers that have a factor in common with 3. Well, 0 does, but we're left with 1 and 2. So there are 2 of them. Suppose I take m equal 4. 0, 1, 2, and 3 are the numbers from 0 to m minus 1. 0 and 2 are divisible by 2. They have a common factor of 2 with m, so cross them out, but we have 2 numbers left. So phi of 4 is 2. Phi of 5, 5 divides 0 and 5, but 1, 2, 3, and 4 are relatively prime to 5. So phi of 5 is 4. What about 6? You look at the numbers from 0 to 5. which have a factor in common with 6. 0 does, 2 does, 3 does, 4 does. We're just left with 0 and 5, so phi of 6 is 2. 7, we look at the numbers from 0 to 6. Which numbers have a factor in common with 7? 0 does, but none of the others do. So all 6 of these numbers are relatively prime to 7. What about 8? Well, if a number divides 8 and it's bigger than 1, it's a multiple of 2. These are the multiples of 2. Cross them all out because they all have a factor 2 in common with 8. But 0, 3, 5, and 7 are relatively prime to 8, so phi of 8 is 4. What about phi of 9? You look at the numbers from 0 to 8. All the multiples of 3 can be crossed out because they have a factor 3 in common with 9. But 1, 2, 4, 5, 7, 8, they're relatively prime to 9. So phi of 9 is 6. Finally, let's look at 10. We look at the numbers from 0 to 9. So any multiple of 2 has a factor 2 in common with 10, so we can cross out all the even numbers. Any multiple of 5 also has a factor in common with 10, so we can cross out 0 and 5. We're left with 1, 3, 7, and 9. So phi of 10 is 4. What about 11 and 12? I'll let you calculate. What is phi of 11? And what is phi of 12? Work it out and let me know. For phi of 11, you look at the numbers and cross out all the numbers that have a factor in common with 11. For phi of 12, you look at the numbers from 0 to 11 and cross out the numbers that have a factor in common with 12. So which of these numbers share a factor with 11?
Zero.
Right? So we can cross out 0. Any of the others?
No, so it would be 10 is the
Exactly.
total.
11's a prime. None of the numbers from 1 to 10 is divisible by 11. And 11 has no other factors other than 1 and 11. So phi of 11 is 10. What about phi of 12? What is phi of 12? So you want to cross out all the numbers that have a factor in common with 12. A factor greater than 1.
So 4 is the total.
Yeah.
So I crossed out 0, 2, 3, 4, 6, 8, 10. Actually, I missed 9, so maybe it should be 5. No, because 3 can go in there. So 9, I crossed out 2.
Right.
So
Any multiple of 2 can be crossed out because 2 divides 12. Every multiple of 3 can be crossed out because 3 divides 12. And we're left with 1, 5, 7, and 11. Those are the only 4 numbers from 0 to 11 or from 1 to 12 that are relatively prime to 12. So phi of 12 is equal to 4. So that's the Euler phi function. And if you look at its values, it's somewhat erratic. 1, 1, 2, 2, 4. It goes up and down. 6, 4, 6, 4, 10, 4. Yeah. So we would like a way to calculate this function. At least it would be interesting if we could do that. And we can begin with a simple set of observations. So if m equals p is a prime, then if you look at the numbers 0, 1, 2, 3 up to p minus 1, you can always cross out 0 because 0 is divisible by p, but none of these numbers is divisible by p, and p has the only factors 1 and p. So if p is a prime, then phi of p is always equal to p minus 1. And that's what we saw in this table. In the table that we just calculated, what are our primes? 2, 3, 5, 7, 11. And for each of the primes, phi of the prime was 1 less than the prime. Phi of 2 is 1, phi of 3 is 2, phi of 5 is 4, phi of 7 is 6, phi of 11 is 10. So whenever there's a prime, phi of p is p minus 1. And we can use the same idea to calculate phi of m when m is p to the power r. R is just, so this is a power of p. So if this is a prime power, then what can we say? A number a has a common divisor with p to the r greater than 1. That means something divides both of these numbers. But the only divisors of p to the r are powers of p itself. So the greatest common divisor of a and p to the r is bigger than 1 if and only if p divides a. Right? That is, if a number divides p to the r and p is a prime, it has to be a power of the prime. If it's greater than 1, if the divisor is greater than 1, then the divisor is a positive power of p to the r. So that power of p, and in particular p, divides a. So if you look at the numbers from 0 up to p to the r minus 1, you want to cross out all the multiples of p. So what are the multiples of p? I have 0 times p, 1 times p, 2 times p. When I get to p to the r minus 1 times p, that's p to the r, that's too big. So this multiple of p isn't on this list, but p to the r minus 1 times p is on this list. So how many multiples of p are there here? I have p to the r minus 1 positive multiples plus 0 times p. I have p to the r minus 1 multiples of p. For example, if I take m equal to 3 squared, which is 9, if I look at 0, 1, 2, 3, 4, 5, 6, 7, 8, this is 0 times 3, 1 times 3, 2 times 3. I have to stop at 8. 3 times 3 would be too big. So there are p to the r minus 1 multiples of p. So those are the numbers that I cross out. So phi of p to the r, I have p to the r non-negative integers, and I throw out p to the r minus 1 of them. That's what phi of p to the r is. which if I want, I could factor out of p to the r, and I would get 1 minus 1 over p. So we actually now have a formula for the value of the Euler phi function at a prime power. So for p prime and r greater than or equal to 1, phi of p to the r is p to the r minus p to the r minus 1, which is p to the r times 1 minus 1 over p. And one of the very important facts about the Euler phi function is that, and I'll prove this, but it takes a little bit of work. So this is Theorem 2.7. Phi of any number m is what? It's going to be m times the product of 1 minus 1 over p over all the primes that divide m. Now, we already proved this for m equal to p to the r, because then this formula simply says phi of p to the r is p to the r times the product over all the primes that divide p to the r. But there's only one prime that divides p to the r, and that's p. So this is p to the r times 1 minus 1 over p. Let's look at m equal to 6. So what is phi of 6 by this formula? It's 6 times the product of all the primes that divide 6, 1 minus 1 over p. What are the primes that divide 6? Can someone tell me? What prime numbers divide 6?
2, 3.
2 and 3. So this is 6 times, when p is equal to 2, 1 minus a half. When p equals 3, 1 minus a third. 1 minus a half is a half. 1 minus a third is 2/3. 6 times a half is 3. 2/3 of 3 is 2. So by this formula, phi of 6 is 2. That's what we saw over here in our chart. Phi of 6 is 2. What about m equal to 12? So what is phi of 12? It's 12 times the product of the primes that divide 12, 1 minus 1 over p. The primes that divide 12 are 2 and 3. So this is 12 times 1 minus a half, 1 minus a third. That's 12 times a half times 2/3. This is 6 times 2/3. This is 4. And again, if you compare this to our table, that's exactly what we got. Phi of 12 is equal to 4. So this is a very powerful result. At least if you're given a number m and you can find its prime factors, you can compute phi of m. So phi of m is an example of what is called an arithmetic function. So this is just a function in arithmetic. An arithmetic function is a function whose domain is the set of positive integers. So positive function f. So it's only defined for the positive integers. You have f of 1, f of 2, f of 3, f of 4. In other words, in another language, it's just a sequence indexed by the positive integers. Function f of n. That's the definition of an arithmetic function. For example, the Euler phi function. It's defined only for the positive integers. That's what it is. And we say that an arithmetic function is multiplicative if it satisfies the following nice property: f of m times n equals f of m times f of n, but not necessarily for all integers, but for all m and n that are relatively prime. So if m and n are relatively prime, and if the function f satisfies this condition, then it's called multiplicative. And as a corollary of this, that f of n be multiplicative if you have a set of numbers, m1, m2, positive integers, that are pairwise relatively prime. That means that if you take any two of them, mi and mj, the greatest common divisor is 1 for all I different from j. Then, if f is multiplicative, f of m1, m2, m3 up to m sub k is just the product, f of m1, f of m2, f of m3 up to f of m sub k.
Professor,
Yes,
quick question. I don't know if this is, if I'm right, but this is something like a homomorphism, right?
yes, it's something like a homomorphism, but in algebra, you don't have this condition that in algebra, you would say this is a homomorphism for all m and n. But here, this is a weaker requirement. This is just for the m and n that are relatively prime to each other. But it is very similar to the definition of a homomorphism. But also here, you don't have a group. The positive integers under multiplication don't form a group. They form a semigroup. But in any case, with this condition, this is weaker than being a homomorphism.
Oh, okay, got it.
But the idea is the two ideas are related. So that's a very good observation. So what we will actually prove is that the Euler phi function, phi of m, is a multiplicative arithmetic function. And I'll show that if you can prove that the Euler phi function is multiplicative, that implies this general formula for the value of phi of m. So by the fundamental theorem of arithmetic, we can write the number m as a product of prime powers. So this is a product of distinct prime powers. And distinct prime powers are pairwise relatively prime. We have pi to the ri and pj to the rj. Their greatest common divisor is 1 for all I different from j. So if phi of m is multiplicative, this implies that phi of m, which is phi of p1 to the r1, p2 to the r2, up to pk to the rk, that's phi of p1 to the r1 times phi of p2 to the r2, up to phi of pk to the rk. But we already calculated the value of the phi function at a prime power. Phi of p1 to the r1 is p1 to the r1 times 1 minus 1 over p1. And phi of p2 to the r2 is p2 to the r2 times 1 minus 1 over p2. All the way up to phi of pk to the rk, which is pk to the rk times 1 minus 1 over pk. And if I rearrange that, I have p1 to the r1, p2 to the r2 up to pk to the rk. When I multiply them out, that's just m. And then I have this product, 1 minus 1 over p1, 1 minus 1 over p2, and so forth. These are exactly the primes that divide m. So this is the product over all primes dividing m, 1 minus 1 over p. So my formula for the Euler phi function is a consequence of knowing the Euler phi function for prime powers, plus knowing that the Euler phi function is multiplicative. So my next job will be to try to prove that the Euler phi function is multiplicative. Right? So it seems like I'm doing a lot today, but again, if you look at the book, this is really just 3.5 pages, and but there is a certain density to the material. There is a lot to learn. Any questions before I continue? So a key to proving the multiplicativity of the Euler phi function is the following result, which is Theorem 2.6 in chapter 2. So we have positive integers m and n that are relatively prime. And the theorem says the following: for every integer c, there exist unique integers a and b such that a is between 0 and n minus 1, and b is between 0 and m minus 1, and c is congruent to ma plus nb mod m times n. Moreover, C is relatively prime to Mn if and only if A is prime to N and B is prime to M in this representation. Right? So this says that I can write every integer C in the form MA plus NB mod MN, where A is between 0 and n minus 1, and B is between 0 and m minus 1. So the proof. So note, there are how many expressions of this form? I have n choices for A and m choices for B. So there are mn integers of the form MA plus NB. And if I can prove that no two integers of this form satisfying these conditions are congruent mod Mn, then they represent Mn different congruence classes. So they represent all congruence classes. So let's suppose we have MA1 plus MN B1 congruent to MA2 plus NB2 mod Mn for some numbers A1 and A2 between 0 and n minus 1, and B1 and B2 integers between 0 and m minus 1. So if we look at this congruence mod n, this is going to be 0 and this is going to be 0. So mod just n, MA1 is congruent to MA1 plus NB1, because this is 0 mod n. But we know this is congruent to MA2 plus NB2, because these two numbers are congruent mod Mn, so they're certainly congruent mod n. And this is 0 mod n, so this is congruent to MA2 mod n. So this means that n divides MA1 minus MA2, which is m times A1 minus A2. So n divides this product. But m and n are relatively prime. So by Euclid's lemma, m divides A1 minus A2, or A1 is congruent to A2 mod m. So if this condition holds, in fact, A1 and A2 are congruent mod m. And similarly, a similar argument would show that B1 is congruent to B2 mod n. So these numbers are distinct. So they represent different congruence classes. And you have Mn numbers of this form, so they represent every congruence class, because there are exactly Mn congruence classes modulo Mn. What about the proof of this condition, that C is relatively prime to Mn if and only if A and B satisfy this? So let C and M and N be relatively prime, and let C be congruent to MA plus NB mod Mn, where A is between 0 and n minus 1, and B is between 0 and m minus 1. So C is congruent to MA plus NB mod MN. So that means MN divides the difference. So M certainly divides the difference. So the greatest common divisor, oh, let's see, how do I want to say this? Let me put it like this. So if C is congruent to MA plus NB mod MN, this means that the greatest common divisor of C and M is the same as the greatest common divisor of MA plus NB and M. So if C is congruent to MA plus NB mod MN, it means C is congruent to MA plus NB mod M. So the greatest common divisor mod M of C and M is the same as MA plus NB and M, which is the same as NBM. Plus, if a number divides both of these, it divides NB, and if a number divides MB and BM, it divides this and this, NB and M. But N is relatively prime to M, so this is BM, because M and N are relatively prime. Similarly, the greatest common divisor of C and N is the same as the greatest common divisor of MA plus NB and N, which is the same as the greatest common divisor of MA and N, which is the same as the greatest common divisor of A and N. These are 1. So C is relatively prime to Mn. So that's the proof of the second part of the theorem, that every number C has a unique representation mod Mn in the form Ma plus Nb. And if C is relatively prime to M and N, A is relatively prime to N, and B is relatively prime to N. So now we can try to prove the multiplicativity of the Euler phi function. So this is theorem 2.7. The Euler phi function is multiplicative. What this means is that if M and N are relatively prime, then phi of the product, M times N, is phi of M times phi of N. That's the definition of multiplicativity. And the proof goes as follows. that M and N be relatively prime. By definition of the phi function, there are exactly phi of M times N congruence classes modulo Mn that are relatively prime to M times N. In general, we know that if A and M are relatively prime and A is congruent to A prime mod M, then A prime and M are relatively prime. So if one element in a congruence class mod M is relatively prime to M, every integer in that congruence class is relatively prime to M. But every congruence class can be represented uniquely in the form. So if you take C plus MNZ, you can write C as MA plus NB plus MNZ. Where C is congruent to MA plus NB mod MN. And we know that C is relatively prime to Mn if and only if A is relatively prime to N and B is relatively prime to M. That's what we proved. So there are phi of A congruence classes with A and M. Sorry, there are phi of N congruence classes A plus NZ with A and N relatively prime, and phi of M congruence classes B plus MZ with B and M relatively prime. So we have exactly phi of N numbers A that satisfy this, and phi of M numbers B that satisfy this condition. So the number of pairs A, B that satisfy both is phi of N times phi of M. Okay. Let me present this argument a little bit differently, because this is, I think this sounds more complicated than it is. So what we proved a few minutes ago in Theorem 2.6, if M and N are relatively prime, then every C can be written in the form MA plus NB mod MN uniquely, and C is relatively prime to Mn if and only if A is relatively prime to N and B is relatively prime to M. And again, A is between 0 and N minus 1, and B is between 0 and M minus 1. So the number of C that are relatively prime to Mn is exactly the number of pairs A and B, where A is relatively prime to n and B is relatively prime to m. The number of A's that you can choose is phi of n. The number of B's that you can choose is phi of m. So phi of mn is phi of n times phi of m, which is the same as phi of m times phi of n. That's actually a somewhat slightly simpler argument than I gave in the text, but you really just look at theorem 2.6. The number C is relatively prime to mn if and only if A is relatively prime to n and B is relatively prime to m. So you have phi of n choices for A and phi of m choices for B. So the number of pairs AB that satisfy these two conditions is phi of m times phi of n, and that's what phi of mn is equal to. Maybe that's a little simpler proof. So if you want to know, for example, what is phi of 120? 120 is 8 times 3 times 5, I believe. Let's see. 8 times 3 is 24. 24 times 5 is 120. Or phi of 8 is 2 cubed times 3 times 5. So by the multiplicativity of the phi function, this is phi of 2 cubed, phi of 3, phi of 5. Actually, we already calculated phi of 8. Phi of 8 is 4. Phi of 3 is 2. Phi of 5 is 4. So this is 4 times 2 is 8 times 4 is 32. Or we could have used the formula phi of 120 is 120 times the product of all the primes that divide 120 of 1 minus 1 over phi. So the primes that divide 120 are 2, 3, and 5. So that's 120 times 1 minus a half, 1 minus a third, 1 minus a fifth. That's 120 times a half times 2/3 times 4/5. That's 120. Let's see, these 2's cancel. I get times 4 over 15. But 120 is 8 times 15 times 4 over 15. The 15's cancel. And 4 over 15 and 4 times 8 is 32. So however you calculate this, you get the same answer because there's only one result. Let me state one more beautiful result about the Euler phi function. Let me do one more example. This is an example in the book. 7,875. Suppose I want to know what is phi of this. This looks hard to calculate. So I need to factor this number. How do you factor it? Well, I don't know. I can certainly notice that this is divisible by 5. And if you divide it by 5, you get 1, 5, 7, 5. And this is again divisible by 5. So this is 3, 5 into this 3, 35. And this is again divisible by 5. This is 5 times 67. And is that right? Something's not right here. 5 times 5 5s are 25. 37, that's right. 5 into this is 3, 1. 5 into 15 is 315. 315, if you divide it by 5, is 63, which is 7 times 3. So this number is equal to 3. Is that right? Still not right. 63 is 9 times 7, which is 3 times 3. So this is 3 squared times 5 cubed times 7. So phi of 7875 is 7875 times the product of 1 minus 1 over p for each of these 3 primes. 1 minus a third, 1 minus a fifth, 1 minus a fourth, 1 minus a sixth. No, 1 minus a fifth, and 1 minus 1 over 7. So this is 7875 times 2/3 times 4/5 times 6 over 7. So yeah. So this is 7875 times, let's see, this cancels, 3 into 6 goes 2. 2 times 2 times 4 over 5 times 7. This is 3 squared, 5 cubed times 7 times 2 to the 4th over 5 times 7. That's 2 to the 4th, 3 squared, 5 squared. This is correct. Let's see, this is 8 times 9 times 25. 8 times 25 is, sorry, 16 times 25. That's 400 times 9 is 3600. So that's one calculation of this using the previous theorem. Yes, alternatively, you could say that phi of 7875 is phi of 3 squared 5 cubed times 7. That's phi of 3 squared, phi of 5 cubed, phi of 7, phi of 3 squared, phi of 9 is, we calculated that. Phi of 9 is 6. Actually, or 9 minus 3. Phi of 5 cubed is 5 cubed, 125 minus 5 squared. Phi of 7, 7 minus 1. This is 6 times 100 times 6, which is again 3600. So these are alternate calculations, but it's interesting how useful that formula is. And the last result about the phi function, which I will prove on Wednesday, I think, is Theorem 2.8. It's quite a remarkable fact. For every positive integer m, the sum over all the divisors of m, phi of d, is always equal to m. Let's look at some examples. So phi of 9. What are the divisors? Sorry. Suppose we let m equal to 9. So the divisors of 9 are 1, 3, and 9. So summation over all the divisors of 9, phi of d, that's phi of 1 plus phi of 3 plus phi of 9. Phi of 1 is 1. Phi of 3 is 2. Phi of 9 is 6. And 1 plus 2 plus 6 is 9. Right? That's what this says. Let's take 10. What are the divisors of 10? 1, 2, 5, and 10. So phi of 1 plus phi of 2 plus phi of 5 plus phi of 10. Phi of 1 is 1, phi of 2 is 1, phi of 5 is 4, phi of 10 we calculated is also 4. 1, 1, 4, and 4 add up to 10. Let's just look at a special case where m is a prime power. So what are the divisors of m? 1, p, p squared, p cubed, up to p to the r. What is phi of any prime power? It's p to the k minus p to the k minus 1. So if I sum over all the divisors of p to the r, phi of d, the divisors of p to the r are just the sum of phi of p to the k, where k goes from 0 up to r. This is the sum from 0 up to r. Phi of p to the k is p to the k minus p to the k minus 1. Well, for k going from 1 up to r, and when k is equal to 0, phi of 1 is 1. So this is 1 plus p minus 1 plus p squared minus p plus p cubed minus p squared up to p to the r minus p to the r minus 1. And you see this is a telescoping series. The 1 and the minus 1 cancel. The p and the minus p cancel. P squared and minus p cancel, and so forth. Everything cancels except this p to the r, and we get p to the r. So our theorem is true for powers of p, and we can extend that argument, but I'll do that on Wednesday to show that this is true for all m. So there are basically two very fundamental results about the, well, three perhaps, about the Euler phi function. It's multiplicative. If m and n are relatively prime, phi of mm is phi of m times phi of n. And for any m, phi of m is m times the product of 1 minus 1 over p over all primes that divide m. And this result. And if you pursue mathematics, you will see that the Euler phi function comes up over and over and over again. It really is one of the fundamental things. All right, well, as I said, this is just a couple of pages in the book, but there is a lot of depth to it. So the more time you spend studying this, the stronger will be your knowledge of number theory. Any questions before we stop for the day? I set up a couple office hours in the evening tonight and tomorrow night at 7:30. I know that for some people it's hard to find time during the day, so I'm trying some evenings and see how that works. I'll also have a couple of afternoons very soon. But again, we start every class with a question period, so you don't have to go to the office hour sessions in order to ask a question. Anything before we stop? No? Okay. All right, that's it for the morning. Everyone take care. Bye.